today a paper, Encode, Think, Decode. So I think this falls in line with a bunch of papers that I already talked about in previous meetings, and I think um, some other guys on the team also have presented papers along these lines. But I thought it would be interesting to explore this paper, let's say, and then I'll share some of my thoughts at the end. So again, we start from the motivation. And the basic motivation is we have some benchmark that wants to improve our model on. Then the common approach is, okay, let's just scale. But what do we scale? We scale parameters, add more layers, increase the hidden dimension. We scale the data, create more synthetic data sets, or we scale the inference time computation. So in this case, you could either have generating more like think tokens, or well, I mean, which is the default approach. So you have this, okay, think step-by-step approach, or you have generate latent vectors, let's say. So I sort of divided this into like discrete thoughts and then latent thoughts approach to chain of thought reasoning. And what's the deal with COT reasoning? So the authors of this paper noted that previous literature, previous works, let's say, they've demonstrated that not all layers are equally effective for chain of thought reasoning or like reasoning in general. So this was a very interesting paper that I skimmed through that made this point. In the original paper, there are a bunch of other references. But basically, not every layer contributes equally to the reasoning process. But then on the other side, the reasoning process itself benefits from effective depth. And basically, effective depth is just, okay, in a single forward pass, how many, let's say, transformer blocks does the residual stream have to go through and get processed by? So that's how busy effective depth in this paper. So from this point of view of the authors, yeah, they basically then explored, okay, the functional role of different layers in reasoning models. And again, leveraging from previous literatures, they were able to divide the role of the layers and transformers into like three different camps, let's say. So early layers, they're capturing general features. So my own personal note here is that this more or less represents approximate functional roles. So at least for me, it's not obvious to me that each group of layers is exactly doing this thing, and other layers are not contributing to like the things I would be mentioning. At least I've not seen any paper made that claim exactly. So it just seems to me that, okay, let's say um, in general, we can always assume that early layers they're contributing to this versus middle layers contributing to this versus late layers contributing to this. You also have the question of, okay, if you have different layers, how do you determine I mean, what's the boundary between early and middle and late? So just a point of note. But yeah, so the functional role of layers, early layers, they're capturing general features. They are doing a lot of knowledge retrieval, picking up facts related to the entities or the like task in itself. Middle layers, they're amplifying task-specific signal. And late layers, they are like capturing more fine-grained features. This is just to say, like in general, early layers are more, or let me say, a very conceptual way. This is not exactly what it is, but a conceptual way I'm thinking about it is early layers are just like dictionary, picking up facts related to the entities or the task specifically. Middle layers are sort of like refining the representation of the tokens relative to this task, and later layers are sort of continuing the refinement, but now continuing the refinement with the goal of, okay, what's the next token that should come? So then the authors noted this in the paper, and the next question they were asking is, okay, how can we take advantage of this specific properties, let's say, of the different layers. So what the authors did in summary was, okay, one, let's decouple the layers of the transformer model. And by decoupling it, you have this, again, early, middle, late distinction. But then also we want to find the layers that are most responsible for reasoning. So they termed it reasoning critical layers. So again, you divide the layers into early, middle, and late. Then you look for the group between early, middle, late that's most responsible for reasoning, let's say. So you have the, so yeah, this is where the, I have a bit of qualms, let's say, with the way the paper represented the naming. So they represented the early layers as like encoding blocks, the mid layers as thinking blocks, then the later layers as decoding blocks. And their justification for this was you can assume that the early layers, they're sort of projecting the inputs, the tokens, the vector of the tokens into this latent space. Then the thinking layers are doing some form of refinements on this, and then the decoder layers, the decoder blocks, is basically like transforming these vectors from this latent space back to the let's say model embedding space. But of course, in practice, it is still the same model embedding vector that is being propagated like all through from the start to finish. So maybe it's just my own conception of what projecting it to latent the dimension means, but like basically it's just the entire transformer block. I just like dividing it into early block, thinking block, and decoder block. But yeah, basically you have this the coupling of the different layers of the transformer into different blocks. So then this thinking block in the middle is where they denoted as the reasoning critical layers, and just basically run your computation through this set of layers, let's say. This image helps to better demonstrate it. So you have the vanilla transformer, just your layers stacked up on top of each other. Then you have this set of layers that are encoding this think, and then you can like basically pass your computation over and over again through this thinking block. Then this decoder block continues the computation. And of course, from this, it's obvious that it is the decoder block that is responsible for projecting to the vocabulary space. So I think a bunch of this were already present in other works. Specifically, I mentioned a paper here, this Gromov et al. So on the unreasonable effectiveness of layers, something like that. But basically, everything so far has still been leveraging prior knowledge, prior literature. So yeah, you have this decoupling into ETD blocks. Then what they did next is, oh yeah, so before we move to what they did next, previous approaches to latent reasoning. The most common thing is, okay, you use the entire transformer as the thinking block. So your entire transformer is like a recurrent unit in itself. Then you're just passing the residual stream vector. Instead of like embedding into vocabulary space, just take the residual stream vector and pass it into the first layer, let's say. So you tease the entire transformer, or you arbitrarily denote the first two layers as encode, last two layers as decode, and the rest in middle as decoder, as the thinking block rather. Or another approach that is quite common is you generate latent thoughts. I think I'm going to talk about this towards the end as well, but this paper specifically, they do not generate latent thoughts. So if anybody remembers in the Coconut paper, you have this forward pass. Then instead of embedding to vocabulary space, you take the last vector of the hidden state, the last vector of the residual stream, then you append it as you append this to the embedding vector instead of like generating a token and then appending that specific token. So in this paper, they do not generate any latent thought. They do not do this autoregressive latent reasoning. It's basically like recursive latent reasoning, basically. So you just take this residual block after all of the forward pass, then pass it again through, in this case, the thinking block. So this is comparisons to the way different papers have approached latent reasoning. A brief summary. So it seems quite arbitrary, like a lot of the choices seem quite arbitrarily. And what this paper decided to do was, again, leveraging on this Gromov et al. Yeah, Gromov et al. They basically realized that if you take the token representation of the token representation in different layers, they have different angular distances. But the insight here is that early on and later on, there are a lot of the variation in the angular distance is huge, but towards the middle, the changes in the angular distance is quite steady, or let's say it's plateaus, let's say. So, and the idea, the summary from Gromov et al. Was that this angular distance is sort of representing the token refinement. So how much is the token vectors or the token representation being refined? Again, this goes back to the idea that the early layers, they're sort of doing this knowledge retrieval and like general task understanding. Then the later layers are doing like this task specific refinement.
I have
So
a
basically,
question.
you have the notion of yeah, sure.
Yeah, so is this angular distance, does it measure the angular distance between representation vectors across different across sequential layers in
Yes.
Okay.
Yes. So I will show the formula later on, but basically you can measure the angular distance across any arbitrary set of layers. But for this specific model, for this specific case, we are measuring across sequential layers. So layers 1 compared to layer 2, then 2 to 3, 3 to 4, on and on to the end. So
Thank you.
yeah, thank you for that question. Yeah. So again, this is a key insight from Gromov et al. That there's a notion of angular distance, and then relating it to the distinction between the different block of layers, let's say, you have also differences in the angular distance that reflects our explanations for what the different blocks of layers are doing. Yeah, so what this paper has done, what the authors here, okay, before I move to that, let's continue this. So Gromov et al. Also noted that on retrieval type tasks, if you remove these reasoning critical layers, you do not get a lot of drop on tasks that are like more retrieval heavy. So tasks that are more like recalling facts, if you remove like the middle layers or you like set the parameters to 0 or something like that, you do not get significant drop in performance. But then if you prune out those layers on reasoning specific tasks like coding, maths, benchmarks, app challenge, you get like significant drop in performance. And again, our metric of interest here is the angular distance between the token vectors. So the angular distance between token vectors denotes which tasks, which layers we prune, which layers we leave. Yeah. So okay, this is strange. But yeah, basically this is the formula for the angular distance. So you have the cosine similarity between consecutive vectors, consecutive layer vectors. Then from the cosine similarity, project it to the angle, then normalized by pi, distance between range of 0 and 1. So yeah, this is basically what this slide is explaining. So what the authors of these papers eventually did was, okay, fine. These layers with stable angular distance, stable in the sense that there is not a lot of variation in the angular distance. Those would be the like reasoning critical layers. Yeah, you measure the angular distance between the vectors. Yeah, so this is basically everything I'm explaining. And then these reasoning critical layers will form the recurrence block from like the image I showed from an earlier slide. So let's see if I can quickly, yeah. So basically this block here is, or let me say, are the like reasoning critical layers from which were gotten from the sorry, give me a sec. Yeah. Yeah, so yeah, so they're basically gotten from the angular distance. Now, of course, because it's recurrent, you are looping over it like k times in this case, some number of times. So yeah, that's basically the encode, think, decode approach. So to summarize again, you have your transformer. Um, you assume the notion of dividing it into encode, thinking blocks, and then decode blocks. Then the question now is, okay, how do you know which layers would belong to which blocks? Then so you measure the angular distance between the so yeah, something I didn't mention actually was the angular distance is between the final token in the context. So you have your assume simplicity batch of one, you have sequence length by dimension. So you're taking the last token in your context in the sequence length. Then you take this vector for this token in layer L, then layer L plus one, then you measure the angular distance between them. Then you do that for like every consecutive layers. So yeah, basically you have this reasoning critical layers, then you just loop over it k times. So that's basically that's summary of the encode, think, decode paper approach. So now we move on to some like experimental config. Yeah, so something I actually forgot to mention was also, I mentioned earlier that a lot of, and I think I'll still mention it actually, a lot of the latent reasoning approaches, it seems to me that their aim is you want to increase effective depth without necessarily increasing number of parameters or increasing number of increasing your data size, basically. So in this case now, the effective depth will move from the number of layers for encode, number of layers for think, number of layers for decode, to you have this k times number of layers for think, because you are basically in a single forward pass, you loop through the think block k times. So basically you have like a longer essentially depth to the model. So experimental config, this was also where the authors of this paper, like the approach was pleasantly surprising. What they decided to do was they decided to integrate this ETD approach into mid-training phase. So you take a pre-trained model before it has been post-trained, then you apply this. So and like the OMO 2 family, I think from Elen AI, if I'm not mistaken, they basically have you have like a series of checkpoints for the different phases, pre-training, mid-training, and post-training. And you have like the training data they use. So you can basically resume the training process from any point. Now, interesting thing is there was no like special data set, there was no special duration of data set or anything. It was the same data that was used for the OMO2 mid training. That's also used for the mid training. And as far as I know, I mean, mid training is not like general purpose training. So it's still like you're still training against you're still training across a lot of domains, but it's more like specialized data, let's say. So basically the only thing that they changed in the only thing that they changed different from the OMO2 mid-training phase was the thinking block itself. So every other thing was the same from the like data mixtures to like every other like training configurations, basically the same. So yeah, this was quite interesting to realize. And then like basically they were evaluating across 17 benchmarks into like a couple of different groups. So there was reading comprehension group, factual knowledge, math, reasoning, multidisciplinary reasoning, common sense reasoning, basically a total of 17 benchmarks. And yeah, this was the main result. So it is also important to realize that if the number of iterations k is one, it's basically like the let's say vanilla transformer without any of the recurrence blocks. So this is the performance of the OMO2 for different iterations of the ETD approach, let's say. So some interesting things to note is yeah, so something I also did mention earlier, I mean, it must have been obvious from the picture actually, but we have particular model, OMO 21B. The range of recursive block is layer 7 to layer 11. So you have the first 7 as the encode, then 8 to 11 as the like recursive block, the thinking block, then the rest as the latent block. So you have this format of 7, 4 times k, or like 5 again, something like that. So because this is going to come up, yeah, you also have it here as well, actually. So yeah, one sec. We've talked about this. Yeah. So if we take a snapshot at 2 iterations with the configurations, we are going to observe that we have the biggest increase in like math reasoning, then common sense reasoning, multidisciplinary reasoning, but then like quite okay-ish performance on factual knowledge. And like basically the authors are trying to buttress, or they're trying to confirm the point that, okay, yes, indeed, this recursive latent reasoning, it's more effective for, again, reasoning every task, not tasks that require some like recall of fact or something like that. So yeah, maths, motivational reasoning, they show the highest increase in level scores. Factual knowledge, big bench hard, showed like minimal gains in performance. General trend, with more iterations, with more Ks, you have better performance. But then the authors also noted that if you are taking performance against iterations, you also have like a very interesting trend. So for example, on this BBH benchmarks, K equals 1, K equals 2, you have almost no gains, but then you start having increase from K equals 3, 4, 5, basically. And if you take a benchmark like common sense reasoning, or factual knowledge reasoning, after like K equals 3, the increase in performance is like almost negligible. So 4.4% increase, 4.8% increase. This 3.57 to 3.74. Yeah, basically the authors were trying to note that different tasks, different task domains, you have different trading performance. And this is basically related to how much correlation is between the task at hand and how much reasoning is required to solve the task by the transformer model. So the authors also compared the ETD approach to 2 of the previous approaches that we talked about. So first one is like use the entire model as the thinking block. So you have 0, then 16 by 2, then 0. So and you can see the performance. Then if we take arbitrarily first 2 layers as encode, last layers as decode, you also can observe the performance. Then of course the OLMO2 itself after the mid-training phase. A detail that was not clear to me from the paper was if they actually carried out the post-training of the OLMO2. So they did not specify, I mean, after their own ETD, if they carried out the post-training, they didn't specify, which was interesting, I think. So yeah, so give me a sec. Ablations on layer selection. So this section, the authors were trying to make their case for why using the angular distance to determine which layers fell into encode, think, decode blocks, why this was like a reasonably informed decision. And basically they ran ablations over okay, I'll mention that towards the end. They run ablations over the first 11 layers. So let's say use first layer for encode, first layer for a second layer for encode, like basically different number of layers for the encode blocks, but they did not specify what they use for the decode block also, which I thought was interesting. But again, just taking the results for what it is, you have the case where the 7th layer, which is the boundary between encode and decode, it was either the highest or like close to the highest, let's say, on most of the task domains. So yeah, basically again making the case for why using the angular distance to determine the boundary was like an informed decision. So yeah, I added this slide like less than an hour ago while I was discussing with let me say Dimitri made a note of some point, and I thought, okay, it would be also cool to discuss this here. Again, so the point here is that different papers, different authors, they're taking different approaches to latent reasoning, and it's quite informed, let's say, to get a sense for what the general approaches are between different it's good to get a sense for what are the distinctions between different latent reasoning approaches. So I think you already talked about the hierarchical reasoning model. So I'll just be like talking about the core differences and the core similarities. And again, so the similarities here is that the recurrent modules, the transformer blocks, albeit they are like encoder only blocks in HRM. Then you have the emphasis on latent reasoning, internal computation, and then both sort of attempts to increase the effective depth of the model. The biggest difference to me seems to be how they perform their recurrence computation, let's say. So in HRM, at the super high level, you have like the, no pun intended, high level module, like the low level module. And then your effective depth is basically the number of steps for the low level thinking module and like the number of cycles for the high level thinking module. So you have this n by t. So and so again, you have this like two components setup, let's say, and in this ETD, you have just like a single recurrence block where you're just passing the same you're just looping the computation over your thinking section, let's say. Another distinction that was super obvious to me was the difference between HRM's training from scratch design to ETD's leveraging pre-trained transformer, and specifically on the mid-training. So I also thought it would be interesting to compare this to Coconut. And of course, the biggest difference is you have autoregressive latent reason versus recursive latent reason. So I think I already mentioned Coconut earlier, but you have this setup where you're just appending the token vector to the embedding and then like carrying out your computation like some number of times before you start generating tokens. So again, you are still like generating these latent vectors, not just in token space. Versus this recursive latent reason where during the recursive computation, let's say, you are not generating anything. You just take whatever the model has represented the input tokens as, then pass it again through the thinking block, k number of times, basically. So, yeah, the thinking block here is also, I mean, another difference is the notion of thinking block. So in the Coconut approach, the entire model is your thinking block, basically. And in recursive latent reasoning, in the ETD approach, you have like a designated set of layers that are like your thinking block. So yeah, basically that's the end of the presentation. I'm going to share some of my own personal thoughts. And maybe this segues to our discussion. So it seems to me that effective depth is representing a new axis of healing. We are not adding more parameters, we're not adding more data. We are just like increasing the computation over a fixed set of parameters, let's say. So I'm finding ways to like do that computation over and over and again. And this is also like let's say I've seen a couple of papers in the last couple of weeks that are basically like drawing the parallels between using the transformer block as your recurrent unit versus using the RNN block itself as a recurrent unit. So I think something else that is, let's say I'll be interested to see is how, for example, instead of having a 20-layer model, let's say, you have a 16-layer model in the case of OMO1B, and you loop through the middle 4 layers like 2 times. So the point is, assume we have infinite compute. Obviously, we do not have infinite compute. Assume we have infinite compute. How does it compare if you just like add more layers, add more parameters to the model versus, okay, you constrain the actual parameters, but you're increasing the effective depth. I don't think I've seen a lot of analysis into that. Another like major theme for how I'm thinking about this, the design space for a well-cooked transformer seems to be quite huge. So, for example, this paper did not mention it specifically, but here the number of iterations that you have at inference, is it the same as the number of iterations you have at training? In this case, for most of the results that they were talking about in the model, obviously they showed k equals to 5, but the main result they were trying to show was k equals to 2. So which k are you using at inference? Is it just your vanilla? I mean, like, do you use just k equals to 1 as in the vanilla transformer during inference? You're using k equals to 2. How would that affect all of the KV caching that you would usually do the prefill and decode during inference? How would this mid-training approach compare to RL fine-tuning? During the RL fine-tuning stage, are you also doing this like recursive latent reasoning as well? Or again, vanilla transformer setup and just like keep sampling tokens from the model? Then this was a very interesting direction. This ETD paper was basically applying the ETD approach to mid-training. Coconut was post-training. Then this paper I saw, I just skimmed the paper. I've not actually read the paper, but it was basically applying this notion of recurrent latent reasoning during pre-training. So it's like looped transformer or something like that. So for me, it was quite interesting to see, okay, like there are so many ways, there's so many things that I could try. So I've, again, the end goal, let's say, is some notion of people, end users, find the model useful for some specific task. The proxy we have for that is benchmarks that hopefully reflect the capabilities of the model on these tasks. Then how do all of these different knobs, different things you could try, how much do they move the performance of the model on like these different benchmarks, these different axes? So yeah, thank you for listening. If there are any questions.
So you do mention that choice of k at inference time, the k may be different from k at training time. Have the authors tried
Right.
changing k at inference time and see if it works at all, or if they can improve performance by increasing k further at inference time compared to training?
Yeah. So like basically, as far as I know, they did not make any mention of k at inference time actually. So for me, those are like some of the questions I had. So even on like the evaluation or the benchmarks proposed, they did not make any mention of which value of k that was used.
Okay. And then
Yeah.
and that question was partially inspired by hierarchical reasoning model because they were the kind of experiment there. And another question is, do the authors compare it to a identical transformer with just extra layers? So basically, same amount of compute as this transformer with a recurrent set of blocks, but
So
replace do it without recurrence, just with extra layers and more parameters.
Yes. Yeah. So I don't think they explicitly did that. The closest I have is here for OMO 2. So like it just took the bare bones OMO 2 after mid-training, ran evals on the benchmark. Then they applied ETD approach. So the effective depth here is not the same as the number of layers of the OMO 2 that is being used, that has been evaluated here. So yeah, basically, I don't think that's such comparison. The closest we had was, okay, you take the model, the original model, increase the effective depth, but then now in this case, the effective depth basically of both models are quite different. So
Right.
I don't know how much of an apples to apples comparison that it is exactly.
Right. I mean, I can see in practice where you may want better performance, spending more compute, but having fewer parameters, and this method is great. But then, if you don't care about the number of parameters, you have a lot of VRAM, and you're compute constrained, then I wonder if having explicit layers instead of recurrent layers actually brings the same or better performance. Yeah,
Yes,
these were
exactly. Those are some of my thoughts as well.
okay. Yeah, these were the only two questions I had. And thank you for comparing with HRM.
Yeah.
I guess I'll add one
Thank you
note.
for suggesting as well.
So with
Uh-huh.
HRM, there was a follow-up paper experiment called, I think it's called the tiny reasoning model. And they actually boiled down
Right.
HRM into a single module. So like even having like these two recurrent modules with different schedules wasn't even necessary. So basically the TRM is
Mm-hmm.
closer to this method. That
Mm-hmm. Mm-hmm.
Anyway, no more questions from me.
Right. Do we have any questions from the other two participants? Maybe write in the chat.
I think Ariel mentioned earlier that the microphone doesn't work, so there probably won't be any questions.
Okay. Okay. Okay, Phil.
And Michael messaged in chat that he has no questions.
Okay, yeah.
Okay, thank you for presenting this method, and thank you for comparisons with the Coconut and HRM. Kind of puts it in
Thank you very much.
context of other methods.
Yeah. Thank you guys for listening as well. Yeah.